So hello everyone. I wanted to go over the problem which is on the quiz. So the purpose of this problem was just to make sure you remember the basic laws and equations and be able to apply simple trigonometry and geometry to solve vector problems. And also be able to properly draw a vector diagram and analyze its components and stuff like that. So if you feel rusty on any of this, take a look at my Physics 201 recap video and let me know if you have any questions. Okay, so back to this problem at hand. So you have two charges. These are the coordinates. There's one a negative charge, -3 microcoulombs. Micro is 10 to the minus 6, so 10 to the minus 6 coulomb. It's sitting over here. The x coordinate is -0.1. The y is 0. It sits on the x-axis. The other charge, Q2, it's +3 microcoulomb. Same magnitude but opposite sign, and this is sitting on the x-axis also. Coordinates are 0.1 and 0. Y is 0, so it too is sitting on the x-axis and the same distance away from the origin. This was -0.1, this is +0.1, so it's symmetric. Then you're asked to find, basically you're asked to find the electric field at this point P. Where is this P? It has coordinates up here. Its x is 0 and the y is equal to 0.3. So let me put that on here. So this P, it has coordinates of 0 for x and 0.3. Let me make sure. Yeah, 0.3 for the y. So it's sitting up here on the y-axis. The x is equal to 0. Now the first mistake many of you made is you calculate for force. That's not what's asked. You're asked to find the electric field at the point P, not the electric force. No matter. So what ends up happening is this is a positive charge. So you have electric field lines leaving this. It's a positive charge. The electric field flies away from those points. This is a negative charge. It's like a vacuum. So electric field lines point towards this negative charge. So it's pulling an electric field as E1, the green vector, like this towards itself. This Q2 sends out a electric field like a wind. That's this pink or reddish E2. It's going out like this. So this is like the basic setup. So the first test of this problem is to see if you can draw and set up what you actually have. So now to solve this, you have to often draw sub-figures because this figure gets cluttered. Draw some sub-figures to find different parts of this problem. So here are the sub-figures. So maybe this is what we need next. Okay, so I've redrawn this. This becomes kind of busy, so I'm redrawing this. So looking at this triangle here, this one over here, I redrew that. And so here's what we have. So here's the charge Q1 sitting on the x-axis, and it's setting out an electric field towards point P, or actually the electric field is directed towards Q1 from point P because it's a negative charge. But this is the right angle triangle that we need to find the distance. So to use Coulomb's law to find a Coulomb force or a Coulomb electric field, you need the distance. It's KQ over R squared. So you need the R. So how far is this point from this charge? The farther away it is, the weaker the electric field. So this is a right angle triangle. This is a legitimate place where you can and should use the Pythagorean theorem. Don't use it to resolve vectors. Okay, so this is the hypotenuse, opposite, adjacent, and all of that. So this squared plus this squared is equal to R1 squared. So there it is, R1 squared. I put in the numbers. This height is 0.3 and this base is 0.1. So R1 squared is 0.3 squared plus 0.1 squared. Then on the other side, and not shown, but over here you'll have your Q2. So this Q2 is same thing. The triangle, it's a symmetric situation. So it's this base is the same, this R is the same, the height is the same. It's the same triangle flipped over like a mirror image. So in any case, this R2 will be the same, 0.3 squared plus 0.1 squared. So these are the distances from the charges. You need that for Coulomb's law, which comes next. So now, Coulomb's law, this gives you the magnitude of the electric field, and it's towards or away depending on whether it's positive or negative. So E1 and E2, notice these are vectors. I have not drawn the bars on top. That means I'm talking about the magnitude. So explicitly it's the vector E1 and you take the magnitude. The same for E2. So these are the magnitudes. They're always positive. And these are equal because you have two equal charges and equidistant. And never mind the sign. We're looking at just the magnitude. So this is given by Coulomb's law. It's KQ over R squared. There is not a third electric charge sitting at the top of this triangle here. So this is basically it. Now you can put in the numbers, and as I mentioned, you don't have to like crunch it out and get a final result, but this is what you have. So K times Q is 3 microcoulombs, 3 times 10 to the minus 6. K is your constant, 9 times 10 to the 9. Then down here, the R squared is the distance. We just found that up here. It's 0.3 squared plus 0.1 squared, so you have that. So this is how strong each of those electric fields are. They're exactly the same, only the directions are different. And this is the magnitude. You can just call it A. This is equation 1. Now that you have the magnitude, the next job is to find the direction of the total electric field. This is where the vector components come in. So here we go. So once again, when it comes to vector, initially we had this figure over here. Things get very busy and your stuff floating in the sky and so on. To analyze vectors, draw the vectors so that the origin of the vector coincides with the origin of your x and y axes. So let's do that next. So here it is. So redraw for the purpose of analyzing the vector. So bring those vectors down here. Here's your E2 and your E1 redrawn with their, the tails of the vectors that at the origin of the x and y axis. And then here they are. It's symmetric. The y component of this and the y component of this, they are the same, but they're opposite in sign. This is positive and this one over here is negative. So the y's will cancel out. As a result, only the x will not cancel. Both are to the left. It's not that one is to the left and one is to the right, causing them to cancel. Both are to the left. So the horizontal, the x component, it will not cancel. So how much is that? So the y components, they cancel out. So first of all, at this point, we can already answer half of the question. They ask you what is the magnitude and direction. So you know the direction. So the direction of the total vector, shown in this proud blue color, it'll be something like this. This is your E net. Okay, so that's your net. This is what you're trying to solve for. Incidentally, you could have also shown the vector addition using the triangle or polygon rule in this manner. So this is your E net. But now to do it quantitatively using components. So here you have the magnitude of E net. What is this here? Yeah, so the magnitude of E net, you want to find the x component. Why does it say this over here? It's along the x. Okay. Never mind. So E net x, we are trying to find the x component of E net. So the x component of the total equals the sum of the x components of the individual electric fields or whatever vectors you have. Forces, it doesn't matter. So each one has a magnitude of A, both E1 and E2. The magnitude is A. What is A? Is this thing that you have over here from equation 1. You can crunch it out and you could have gotten a number, but that's A. So leave it as A since you're not using a calculator. But then the x components are a magnitude cosine theta, magnitude cosine theta. So E1 and E2, they're both A, but the thetas are different. Let's look at the theta. So here are the theta. So here also, I think some of you had angles all over the place. These are the official angles. Before determining the angle of a vector, make sure the tail is sitting dead center on the origin. And then you start from the x-axis and you go around until you're pointing the thing along the vector. This is the angle from here to here. So therefore, this pink or reddish thing, that angle that you have here, that's for theta for E2. So this from here to here, this is the angle for the vector E2. And for vector E1, you start from the x-axis, you go counterclockwise, keep going until you come to that vector. This is that angle. So the angle theta for E1, it looks like it's more than 180 degrees. So now, so what I've done here, so this angle over here, let me call this angle alpha. If this angle is alpha, then this green theta E1 is going to be 180 degrees plus the alpha. So theta E1 is 180 degrees plus the alpha. The other one, you have to back up by alpha. So instead of going all the way to 180, you have to go to 180 and come back by alpha. So these angles are alpha, by the way, alpha. Okay, so those are alpha. So theta 2 is 180 minus alpha. And if you needed to find that number from this triangle, you can find it. Opposite over adjacent is the tangent of alpha. So alpha is arctangent of 0.3 over 0.1. So there it is. So this is alpha. And so that's it. So the whole thing is solved now. This is the net electric field. This is the magnitude. It's A. What is A? It's this number over here times cosine of theta 1. What is theta 1? It's 180 minus alpha. Theta 2 is 180 plus alpha, or the other way around actually. And then if you need to find alpha, this is the alpha. So just a crunch over here, crunch over here. With these two crunches, you basically not only have a firmer abdomen, but you'll be able to solve this thing numerically. You'll have the final magnitude for the whole thing. And as we said, the direction is pointing in the minus x direction. It's at 180 degrees. So that's basically it. So this concludes the discussion of this problem. If you have any question, let me know.